Good afternoon, ladies and gentlemen. It's my great pleasure to make this presentation today. I'm Hong Zhao Chen from a master student from National Science University in Taiwan. And the title of my study is Predicting Dielectric, Mechanical, and Thermodynamic of Properties of Low-K materials using deep learning potential. And this is the outline of my presentation. First, I will introduce the background and motivation of my study. And next, the simulation method and model of this study will be shown in this part. Then I will discuss my simulation result in detail. And finally, introduce the future work because some parts of my study are still going on. Nowadays, with the improvement of fabrication technique, the miniaturization of electronic device or products has become feasible, which adopt more transistor nodes on a smaller integrated circuit IC. Disconnecting two or more IC components are isolated from each other by interconnect isolated material. Consequently, minimizing the interconnect size is one of critical technologies for device miniaturization. And so far, many research has focused on reducing the resistance of scale interconnects. And it is technically challenging to deposit integrated dielectrics at low temperature. Compatible with complementary metal oxide semiconductors, interconnect isolation materials must have a low relative permittivity as long as dielectric constant acts as a diffusion barrier against metal migration into the semiconductor and be thermally, chemically, and mechanically stable. Reducing dielectric constant, the method of increasing porosity is often used, but the mechanical strength will also decrease. And low-K materials need to withstand the temperature used for interconnection manufacturing, and this temperature can often reach 400 to 500 degrees Celsius. For the polymer that construct low-K materials, they may start to decompose before reaching the highest temperature. So it is very difficult to have good enough thermal stability. So, we choose boron nitride as our low-K materials because of its good mechanical, thermodynamic, and dielectric properties. And some studies have found that amorphous boron nitride has an extremely low dielectric constant of 1.78. So we use molecular dynamic simulations to make change to the structure and calculate its properties. Molecular dynamic simulation is a powerful tool for studying molecular behavior at the atomic scale, and several classical potential functions for boron nitride have been developed. However, these potential functions do not apply to our case. And just like Turtlesoft, Turtlesoft is only suitable for two-dimensional materials like hexagonal boron nitride, and the extet function is applicable to hexagonal boron nitride and QB boron nitride. However, none of these classical potential functions can describe the relationship between multi-layer boron nitride, layers to layers. And the boron nitride data we download from the website material projects, and the required properties will be obtained through density functional theory (DFT) calculation. And these are isomers of boron nitride, and each structure will randomly move the atomic position plus or minus 0.05 angstroms to obtain more structure. Then calculate self-consistent field by DFT to collect the required property. And these are two methods that we will use in molecular dynamics simulation. The initial hexagonal boron nitride model is randomly sampled by Bayesian hoping method to find the most stable structure with the lowest energy. And this method greatly improves the efficiency of the simulated annealing method. And Bayesian hoping is an algorithm in which structure perturbation is followed by energy minimization. And this process effectively changes the potential energy surface by removing the high potential barrier. So we use this method to create amorphous boron nitride in the form of simulated annealing of hexagonal boron nitride. And the process is first convert the information into length formats. And in order to find the most stable structure with the lowest energy, the Bayesian hoping method was applied to obtain the most stable absorption structure. And the two method is non-equilibrium molecular dynamic. And the NEMD method is used to calculate the thermal conductivity. The first step is to convert the information into length formats, and next the heat flux in one direction will be set, and then calculation will be made based on the temperature difference caused by the heat flux and converted for formula. Finally, the thermal conductivity will be calculated. And DeepGen is a software based on DeepMD kits, and it is a scientific software for developing deep learning potential using deep learning molecular simulation method. And using DNN training data after training, it can not only accurately reproduce the energy and force in the training data sets, but also accurately predict the structure and dielectric property of materials. First, multiple sets of non-X and Y data are collected, and both are fed into the machine. Through the training of more complex neural network, machine can generate neural network models that can explain the relationship between X and Y. If you throw any new X into the model, you can get a predicted Y. Therefore, this project will use the deep learning potential after training with the deep neural network method. And it can overcome the disadvantage of potential energy. And the result is close to density functional theory. And this project will use deep learning energy to simulate amorphous and non-metallic. Comprehensively compare the accuracy of potential energy and deep learning potential energy and predict mechanical property. And by the Bayesian hoping method, we can convert the hexagonal boron nitride into amorphous form and calculate the property of amorphous boron nitride, like potential energy, force, as training data for deep learning. by DFT SCF. And finally, the deep learning potential trained by DPGen is obtained. And the result after DPGen training can be seen from figure 8. As the number of training states increases, the loss function gradually becomes smaller and finally converge, which means that the learning trend is good, and it can be seen from figure B that the training of force is also good. Both the initial calculation value and the predicted value after training are very similar, and the same situation can also be seen from figure C for energy. And after 200,000 states of training, we can see the force and energy of the validation RMSE and training RMSE. It should be noted that the force RMSE after training is relatively large. This may be because our data is not perfect enough. The change of force at different temperature cannot be fully described, so resulting in higher training RMSE. And finally, using the trained deep learning potential energy, several different structures were simulated by molecular dynamics, like MVT and MPT symbol, and all show structure stability. And we will do more MD in the future for verification. Okay. And in the future work, we will prepare more data to achieve our expected force RMSE and add more factor to make the data more complete. And after this, we will calculate the thermal conductivity, dielectric constant, and mechanical property to compare with the experimental value to verify the accuracy of my study. And finally, we thank National Science University and Ministry of Science and Technology of Taiwan. And this photo shows our lay members. Thank you for your listening.
Okay, thank you for the presentation. Do you have any questions? Okay, please.
In your can you also change some structure of the light? Can you change the structure of the whole light?
Yes. Yes.
How can you do? How can you change the structure of the?
Just using the basic photon mass is a molecular dynamic method, and it will find the lowest energy, and the structure will change in the same time. Yes. Okay.
Okay, any other questions? Okay, let me ask questions. In the introduction, you talk about BH and NEME simulation method.
Yes.
Would you tell us about the pros and cons of these two methods?
Can you say?
Strength and weakness of these two methods when you compare the simulation method. How these are different between BH and NEME method?
Yes. BH is to change the structure, and NEMD is for calculate thermal conductivity.
Oh, okay,
yes.
got it. Different method.
Yeah.
Okay. Okay. Do you have any other questions? If not, please give a thanks to the speaker. I'm going to deliver the certificate achievement in honor of your presentation. Thanks. Do you photo?
Yes.
Okay. Thank you. Okay, second speaker is from South Korea.